Hey you folks, Cool18 here, and welcome to another episode of our Unity 3D tutorial on making a tile-based moving thingy like you would find in Civilization or a roguelike dungeon crawler type thing. We want units to move along a map and pathfind around obstacles and that sort of thing. We've basically got everything in place for us to go ahead and write in Dijkstra's algorithm here, which will allow us to find the shortest path to a destination. So what I'm going to do is I'm going to start translating the pseudocode into our little C# environment here in our move selected unit 2. So we need, one of the things we sort of kind of need to do is translate what? What? Well, we need the start node and the end node, actually, is what we need to do. So if we look, where did my thing go? Oh, hold on, I forgot I gotta resize this window because otherwise it's gonna hide it every time. There we are. So there clearly are some arrays, this distance array and a previous array. Doesn't really describe it. I find that a little fuzzy sometimes. You gotta like figure out and backtrack to see exactly what a reference is. But they have an array that they use that tracks the distance traveled to get to any node and what the previous node in the sequence would be. So we've got two arrays we have to create. One called dist and one's called prev. So we're going to go ahead and do that. And what are they? They are lists of nodes. Or they are dictionaries. They're not, there we go. They're not lists. They are dictionaries where we can pass it a node. We can say something like, hey, the distance to some node is equal to 10 for whatever reason. So we want that sort of structure. So it's going to be a dictionary where the key for the dictionary is going to be a node. And the value for it is going to be a float for our distance. And we can initialize this, new dist. Why the hell is it doing that? There we are. Okay. New dictionary. We're going to need another one, which is going to be very much the same. Dictionary. The key is going to be a node. And the value is going to be another node. And this is going to be prev, previous. New dictionary, this one here. All right, we've got those set up. Now what it wants us to do is it wants us to set the distance for source to be 0 and the previous node for source to be unidentified or undefined, which is null. Source in this case is where we're coming from. Note that there's no goal right now. Source is where we're coming from. Well, we are coming from where our current unit is. Well, we know we have our selected unit. And it's got a component on it called unit, which has a tile X and tile Y, right? So our source, the source, hell, we'll call it that. Our node source is from our graph. It's our graph at coordinate tile X, comma, tile Y. I'm going to do this as a one-liner because we can make it maybe look a little fancier if we say it's our graph at tile X, tile Y, like so. That's our source. That's where we're coming from. So in our dictionary, which right now is empty, which is fine, we're going to populate it. We're going to say distance source. Obviously, the source is 0 distance from itself. To go from the source to the source, it's 0. And prev, this is an array that, or a dictionary that contains the chain of nodes you have to walk to go from one tile to the other. Well, the way you walked from source, well, there's no previous. It's the end of the line. There's nothing more early in the chain than the source, our original tile. So we just set that to null. Undefined is null in C#. Okay, now we're all right. Now we're going to keep going to the next line. Let me maybe shrinkify this a little bit like that. So now we have some sort of loop. For each vertex named V in graph. Well, we're using the word node, right? But nodes are our vertices. That's fine. So we can say, hey, we've got a for each keyword, construct, whatever you want to call it here. For each node V in graphs or graph, we can do it that way. Well, we sort of have a, can we loop through it that way? We don't have to do a for x equals 0, y equals 0 thing. We might be able to iterate it through this. We'll see if it works out. If we do this, actually, let's see. Do we get a syntax error? No, everyone's hunky-dory. Okay. That is good to know. All right. So for each vertex in graph, we're going to see if V is not our source, then, oh, this is where we initialize. So we're initialize everything to have infinity distance, since we don't know any better right now. Also, it's possible that some nodes can't be reached from the source, which would make infinity a reasonable value. So what we're going to do is we're going to populate the array. We've already populated the source one, and then we're going to populate the others. Technically, we didn't have to do this here. We could have done it here as an else, but this is going to be fine. So we're going to set the dist of V to be equal to, we do have an infinity that's handy, which is this. Just sets it to the highest possible float, I think. And then we're going to say previous of V. Oh, really? It's prev here and previous here? Wikipedia. What are you doing to me? We've got a prev and a previous. You're killing me. Is it previous everywhere else? It's previous everywhere else. Wow, that's unbelievable. I'll keep it prev because that way we have 2 4-letter words there. And there's some 4-letter words I want to say to whoever wrote this stuff up. So we're going to say no. You know, we don't know what node comes before it in the chain. So I think it's pretty obvious. Like, we didn't necessarily need to set this here. We could have set this all inside of here and whatever, it's fine. And then we're going to add V to Q. What is Q? Q is our list of unvisited nodes. Okay. And literally, it will just be a list. All right, so let's go ahead and set up one of those up over here. I'm going to set up a list of nodes, and I'm going to call it unvisited. These are nodes we haven't checked yet. New list of nodes. So set up the queue. The list of nodes we haven't checked yet. All right? So that every node we haven't checked yet will be inside of unvisited, and we're going to do that here. We're going to add, or unvisited dot add V. Note that everything gets added to that, including our source, right? So everything gets added to that. Next up, while Q is not empty. Okay, all right, that's easy to do. So while unvisited, which is our Q, dot count is greater than 0. We're going to do some things. So while we still have some nodes we haven't checked, we're going to keep looping through. Easy peasy. Next, we're going to grab U, which is going to be another node. Okay, let's do that right away. Node U is equal to what? The vertex in Q with the minimum distance. And I like how it's self-referential. We've got a U here and a U there. I'm not sure I agree with how this is all written up. I don't know. Maybe, for all I know, this is the original, and it's just never been updated from this. Dijkstra originally wrote it. So, vertex in Q with the min distance. So, out of all the unvisited nodes, we want to grab the one with the lowest distance, which on our very first loop through will be our source. I mean, everything's going to have a value of infinity, and our source will have a value of 0. So our very first time through, we're going to be grabbing our source. So how do we grab the thing in unvisited with the lowest possible distance? Well, we could just make a loop, right? I could do that. I could loop through them all, find the one with the smallest number, and then call it done like that. And that's fine. I'm going to take a slight shortcut, though. What I'm going to do is I'm going to go and add in another library over here, system.link. This thing is awesome. It adds a bunch of little helper functions basically on your various arrays and whatnot that allow you to treat them almost a little bit more like databases and makes your life a little simpler. Because what we can now do in our unvisited nodes, we can say that we would like to grab the thing with the minimum value. So I'm going to bring up the documentation for that. Link min. Oh, this is not the documentation. Does not min just do what I want? Yeah, I've done the order thing before, which is a little bit slow. Maybe, yeah, maybe it's a good thing that I accidentally Googled up the Google up the wrong thing here. Because we could just order it and then grab the first one. It's slow. All right, let's do it. It's fine. So we're going to order by. So out of our nodes in here, we're going to return n dot. We're going to return the distance of the node. So all the nodes inside of Unvisited, we're going to order based on their distance in the distance array. Everything's been initialized. Everything exists in here. So we're going to sort through all that. And then after it's been ordered, we'll grab the first one. This is not fast. It's not fast. But it's short. You might want to use some sort of priority queue system or something like that where Unvisited is always in the correct order. That's probably slightly more optimal. Consider having Unvisited be priority queue or some other self-sorting data structure. Self-sorting, comma, optimized data structure. For our purposes, this should work fine. It should order it, ordered where it's going to be going 1, 2, 3, 4, 5, 6. So the first thing will be the smallest number out of that. So this should indeed, the first time, return the source, which is okay. We then have to remove u from q. Well, so unvisited dot remove u. All right, there we go. We can do that. Next, for each neighbor v of u. Okay. First catch here, we can't really use the v again because we used it over here. There might be a way, because here's the problem. If I try to use another, so if I try to do something like for each node v in u dot neighbors, which is what it's being asked to do here. If I do that, I'm pretty sure we'll get an error because we're using v twice. Apparently I'm wrong. I thought it would complain about this. Maybe because they're each in a for each, it's satisfied. Because it always weirds me out that there's no, the local scope doesn't work the same way in C# as some other languages. There must be something special with the for eaches. The other thing that annoys me is I can't say something like node v and then for v in graph. I'm pretty sure that's not legal. Yeah. Type and identifier. So there's, the for each is special in a way that still squicks me out compared to certain other languages. But apparently this is going to work fine. Okay. Good stuff. So for each neighbor, so all of u's neighbors, we're going to loop through each one, and we're going to grab, there's going to be a bit of a temporary variable called alt, which is going to hold the distance. So we're going to grab the distance of u. Keep in mind that's going to be 0 the first time because distance u, or because u is going to be our source. So this is going to be 0 the first time. And then the length of u comma v. Well, okay, what this really is it's a distance of these two vectors. So u and v both have a position, and we know what they are. Actually, I say that. I don't think the nodes are self-aware of their own position. No, so we're going to need that information. Yeah. We're going to need that information when we create all our nodes. That's kind of annoying. No, that's just the reality of it, though. Okay, public int x, public int y. So when we loop through all of our nodes over here, we're going to have to say, listen, graph x, y, dot x equals x. Our nodes have to be self-aware of their position, because then what I can do is make a little helper function over here. Public distance to, and it'll need another node called n, maybe. Oh, it'll return a float. And what it's going to do is it's going to return the distance between the two. I wonder if it's faster if I just use the vector2 helper. Sure. Return, so vector2's got a helper called distance, which is going to do the math for us, and it needs two vectors passed back into it. So we'll say vector1 is going to be our current xy, and vector 2 is going to be the secondary nodes x and y. So this will return the distance between two nodes. So if we go way back down here, we've got our zero distance plus our node u dot distance to v. Now, we do have to talk about something again. Is this the way we want it? This is going to return the Euclidean distance between two nodes. Remember way early on in the first video, I hit play. Yeah, I was going to say it's probably going to crap out on me here. Just return right away. Don't actually run. There we go. What is the correct distance from here to there? Well, it depends on your game, right? This will return the Euclidean distance, which is going to be the square root of 2, which is what, 1.1, yada, 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 yada. So right now, it'll tell me the distance from here to here will be 1.2, which may or may not be correct. Now note that for pathfinding purposes, the distance here is not the same necessarily as the movement cost. I can leave it in here. That way, it'll generally prefer going in straight lines. Because one of the weird things that can happen, let's say I'm trying to pathfind from this tile here. Oh yeah. From this tile here to this tile here. If the movement cost for diagonals is just equal to 1 in the pathfinding system, it's entirely possible the pathfinding system will suggest we do something like wiggle, woggle, wiggle, woggle, wiggle, 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 wiggle. And technically, that will take just as many turns as if we just gone straight to the left and then up 1. But it would look stupid. So I'm going to go ahead and accept the fact, even though in my game I'm going to have them move on diagonals and have it only cost 1 point of movement, even though that's the case, I am going to have this distance to still return the actual Euclidean value, just because it will tend to return paths that are straighter and use less diagonals. It'll look better. But it entirely depends on your game, exactly how you want to work this. But I'll leave it in for now. Okay, so we are going to grab this new calculation. We're going to stick it in this thing called alt. And then we're going to check to see. This is the value based on the current path we're walking. And again, the first time it's a little weird because we're currently in, we're just looking at the first node. But at this point, we're bumping into a new node. Or we're bumping into a node, and we want to see, is the distance based on the current path we're working out, is it shorter than any distance that's already been calculated for this node? So if alt is less than the distance of this new node, then what we're going to do is we're going to set this as the new distance to this node, and we're going to say this node, which maybe we already had a path, but this is a shorter path. The shortest way for the node to work is through U. So what we're doing is a situation. Is it going to run? It is going to run. So we've got some source, and we've got, some tile over here. And somehow maybe we've already bumped into this tile, but we went some crazy route, and it's got a cost of like 10. Well, now we've just happened to calculate a slightly different route over here that makes it slightly cheaper to go this way. It only has a cost of 8. So now we're telling it that from this node, instead of this being the previous, right, which could happen on various sneaky paths and depending on how diagonals cost, instead of saying that from here, like this is the previous node in the chain, we're going to say, no, from here, this is the previous node in the chain, because it's a slightly shorter distance. So we're going to go ahead and update that. That brings us to the end of the if, and then the end of the for, and then the end of the while. And then this, by default, the normal algorithm returns the full set of all distances and all previous nodes. It calculates from our source node what the distance is to every single node in the entire map. That's not what we want. We can stop following this now. And what we can do is actually look at this particular discussion over here. If we are only interested in the shortest path between vertices source and a target, we can terminate the search at line 13 if u equals target. So let's talk about that. Do we have a target? Well, it's this. So we have a source node, which is this one. We can also, at this point, create a target node. And a target node is x, y. That's our target node. So at line 13, it says, line 13 in this code is right here. That's doesn't make any sense. Line 13 would be here. We're not in the middle of a loop. It should be here. Something is weird. Has this been edited, the pseudocode? I gotta check the history of this thing. I feel like someone's been mashing things up. Something doesn't make any sense. Let me just check my own reference from the last time I implemented this. Give me 2 seconds. I actually already had it open just in case I was having a silly moment. So, get path direction. Where was my actual pathfinding? There it is. If I check my old code, this is for my Ludum Dare entry actually. Last time I put this in. 2, target 2. Yeah. It should be right after here. Which is line, yeah, which I'm right. It should be after line 15. I think I'm gonna have to go and make a Wikipedia edit. So what we do is we grab the out of all the unvisited nodes, we grab the one with the shortest distance still left in there. And if that one, if u is equal to our target, then we can break out of the while loop. Because we have our information. This is weird. First of all, there's the prev versus previous. And then there's the fact that this line number is not correct. How weird. Okay, sure. Let's move on. We've got this. This is really, really, really not optimal. You know what? This is driving me crazy. Because what we're doing every time, we're sorting the entire array and then grabbing the first one. We can be a little bit faster over here. So we're going to have our u, which we'll just start off as a null. For each node possible u in unvisited nodes, if u equals null, so if we haven't found a u, then we can grab that here. What we're doing ultimately, we're just setting u to be equal to possible u. If we don't have a u, then we can grab the first one, that's fine. Otherwise, if the distance between the possible u is less than the distance of u, yeah, then we do that. Okay, that is way faster. There's possibly still ways to optimize it, but honestly, this is probably as fast as it goes. So u is going to be the unvisited node with the smallest distance. The first time through, the only thing that has a non-infinite number is going to be our source. But then after that, everything that's neighbored to our source will get a new distance calculated. So the second time through, what it's going to be doing is grabbing one of our neighbors and putting that in, and so on and so forth. Okay. So u is going to be the unvisited node with the smallest distance. It's going to grab that. If we happen to find u is equal to a target, we can break out of the while loop, right? Exit the while loop. So at this point, if we get here, then either we found the shortest route to our target, or there is no shortest, or there is no route at all to our target, which is possible. How do we check to see if there's no route at all to our target? If distance of our target is infinite, no route to our target. Or actually a better thing, because I don't like comparing floats, if prev of our target is null, then there's no route that goes from our target that can backtrack to our source. And that's the thing, this list will be kind of inverted. These prevs will basically, you start at our target and you backstep through all those things until you get back to the source, and that will be how you get there. Basically, there's no route between our target and the source. So we probably just want to, I don't know, return here or something like that. But then we get to this point and we have one. We know we have a legal route to our target. So what are we going to have to do? Well, what we're going to want is, we're going to want another list. List of nodes. Probably okay. Which is the current path, which is going to start off being null. What we're going to do, since we know we have a legal path, we're going to loop through each one of these targets and add them to our current path. For our current path, we're going to set a new, going to be a list of nodes, and then we're going to make a new placeholder, some sort of new node, cur node, which is going to start at our target. Am I right? I think I'm right. While prev cur not equals null, while there's still a previous node to step backwards through, we're going to add our current path. We're going to add, hold on, actually let's switch this. While current is not equal to null, we're going to add current. Then we're going to set current to be equal to the previous node in the chain, like so. Step through the prev sequence chain and add it to our path. Right now, our path describes a route from our target to our source. So we need to invert it, which we can do very simply because we still have that link component. So we can say reverse. There we are. So once this finishes, this move selected unit 2, what it's not doing is it's not actually moving the unit anywhere. It is simply populating this current path object. In fact, what we should do at the start over here, get rid of this old code, set it to this, set current path to be null. We're going to clear out everything, and we're also going to rename move selected unit 2. I'm going to hit F2. I'm going to do this. It's going to be generate path 2. We're going to do that, and that should update the other script at the same time. Unreachable code detected because I left in a return at the top. Hit play. Got an error. Line 83. Object reference not set to an instance of the object. Oh, right, of course. That's an important thing. Graph XY, I have to tell it, new node. There we go. Actually, I have to make a node there before I start stuffing things inside the node. Play again. Good stuff. Now, if I click, nothing should happen. Hopefully, there won't be an error or an infinite loop. Okay, we did get an error, no infinite loop, which is nice. Object reference not set to an instance of an object. What? Make a new vector 2. Am I getting past a null node? I think that's what it's complaining about. I think this node... We're calling distance 2, and I think we're passing it a null. Why would that happen? It should never happen. V should be valid. Hmm? If n equals null, debug.log error. Huh? It should only get called one place, and it should never not be a thing. No, we definitely got a WTF. Okay, so here's the question. We're looping through a list of neighbors, and we're checking the distance to the neighbor. The only thing that could be happening here is if u.neighbors is null. Oh, right, of course. Of course, of course, of course. We populate the neighbors here, and we're adding stuff based on the graph. Well, we could be adding stuff here that are not initialized, because it only gets initialized here. So we actually have to loop twice. Bear with me, I'll explain in a moment. Close that. Bring that over here. Actually, we can do this. Initialize the array. Initialize a node for each spot in the array. Now that all the nodes exist, calculate their neighbors. There we go. So yeah, we're putting a bunch of nulls inside of this neighbor array. So this should now, no, wherever my node thing was, this should never, ever, ever, ever happen anymore. It only gets called once, and it should be created. There we go. Now, nothing is happening, which is awesome-ish. But what should be happening is we should now have a path. Again, it is worth noting that everything that we're doing is based sort of on the predicate that there's only one unit, because this this path right over here, which I could move up. Right now, we are assuming we only have one unit. So this is being... why don't I just do it right? As I say, so this is being saved in the map. But if we had multiple units, obviously this would not be good. So why don't I have a unit thingy over here? Why don't I do something? I can give it a path. Like that. Now it doesn't know what a node is, because node is a class that belongs to my map data. So what I could do though is I could make it public, and then this actually becomes tilemap.node. Oh, it doesn't know what a list is because we didn't include generic. There we go. So now each unit can have their own path. But this thing, which is generate path to, first of all, tries to set a null path and also doesn't return anything. Let's change this so that it returns a list of nodes, which is the path. So we'll set that, like that, and then we will return current path. And then most importantly, actually, we don't return it. Never mind. Wait. Void this out. We don't need to return it. What we need is our selected unit dot get component unit dot current path, which is not public, which we need to do. We want to set it to this current path we just calculated. There we go. So after we calculate the path, we give the unit the new calculated path. And actually, I will have to go back up to the top here and clear out its old path. Clear out our unit's old path. So by the end of it, either it will fail, in which case we'll just jump out here, which means the path will still be just set to null because it's got no way to get there, or we're going to go and set it to the correct path to get there. In the next video, what we will do is we will have our unit actually step through this path step by step. Now note at this point, we are going to be ignoring mountains. So if I go and I click here, the unit should go 1, 2, 3 and ignore the mountains. We'll see. Hopefully that exactly is what happens. And then we'll start to add in things like unwalkable terrain. But that'll have to wait until next time, folks. Thanks for watching. Bye-bye.